Well, good morning, everyone. My name is Patrick Booth, and I've been working with the team at Safe Software and using FME for research in mine gas emissions and safety for about the past 7 years now at the University of Wollongong, which is about 80 kilometres south of Sydney in New South Wales. Today, I'll be presenting how FME has facilitated an improvement in mine safety by allowing really an unprecedented alignment of the theoretical, laboratory and field research that we've been undertaken here at the university. Just firstly, I'll acknowledge the local traditional custodians of the land that I'm broadcasting to you from today, which is the Darral country in Wollongong. And I pay respects to the Aboriginal elders past and present as the knowledge holders and the teachers. A little bit about me. I'm actually coming from a trade background. I'm a licensed electrician, worked my way through various engineering positions and project directions for a number of international resource and environmental projects, but specifically in the areas of greenhouse gas emission reduction and energy conversion, particularly of the mine gases to electricity. As a consulting engineer and more recently a business owner and recently graduating with my doctorate here at the university, FME has allowed our business, which is MeCee Solutions, to offer a really unique and experienced blend of the engineering, commercial, project and operations management services into the resources and the energy sectors. By remaining platform agnostic, our services can really be tailored to meet the individual client needs, and we can deliver appropriate leading edge technical solutions combined with the commercial and operational support to ensure that those business challenges are resolved in a safe and sustainable fashion. Oftentimes, particularly recently, we're providing linkages between renewable energy generators who are wanting to build, own, operate physical energy supply assets, particularly in the solar and wind sectors, to help them earn a commercial return and also allow end users who desire certain commercial and sustainability outcomes for emission reduction and lower costs of their energy to really meet their needs. In the last decade, over 750 lives have been lost in underground coal mines around the world as a result of methane gas explosions and gas outbursts. The research problem that we've been working on here at the University of Wollongong is that current gas emission prediction tools, particularly in that dynamic energy space, are really limited in the application due to their spatial and time-based resolution, which is generally at best at regional scale. So the objective of our research is really to develop high-resolution dynamic model for transient gas emissions, particularly those that occur in the case of outbursts, and predict those from underground coal mines based on site-specific conditions. The fugitive emissions of gas from underground mining, and particularly in the ventilation air, not only contribute to greenhouse gas inventory, but in the case of methane also represent a massive opportunity for energy recovery. The gas reserves that we typically extract are typically not just limited to the economically recoverable seams, but also include coal measures that are both above and below the working seam. In many cases, those risks that are identified much later in the mining cycle, where remedial action is typically more expensive and is also more likely to incur production delays or loss. As the mining progresses to greater depths around the world, most of those gas emissions will increase beyond the practical management capacity of ventilation and our current pre- and post-drainage systems. Using the traditional approach of just increasing the ventilation quantity is unlikely to be sustainable. So today I'll be running through how FME has been used to treat the data from the mine sites and from regional scale in multiple different areas and at multiple different scales. And what did we learn around our journey? Well, really, a data-driven culture is key. Most of those, fundamental principles that are involved in the calculations of gas emission and gas emission prediction really rely on accurate, timely, and resolute data. And that's where FME has really helped us to automate all of the hard work and the heavy lifting, but while also being platform agnostic, so that we don't get locked into particular vendor platforms and we're not limited by the particular platform or the systems or the softwares that particular mine sites are using. Today, I'll give some examples using 3D visuals, some of the digital elevation models and raster-based processing that we use, also some of the lab and the CAD data that we clean in order to provide a really good foundational data model to allow timely and accurate analysis and consistent analysis of our results. I'll also demonstrate some of the CT images that have been used at microscopic scale with the help of FME to really visualize the certain properties and the materials properties that are contained in that coal at very, very low resolutions, which are typically needed to analyze these emissions correctly. And finally, I'll be going to explain how democratizing that data and driving those decisions with data and also maintaining the operational flexibility is key. And FME can help with all of that. The iceberg is a typical sort of model of visualization of the amount of effort that's actually required to integrate some of these systems, and it's no secret that a lot of the work happens really under the covers. Up to 90% of the effort is involved there below the waterline, and the iceberg model is a really good representation and visualization of how much work is actually needed to configure these data correctly. Data reporting and the presentation layer, which is the thing that is surfaced and most people see, it really relies on the robust and repeatable data systems and processes under the covers. And that's where FME really comes to the fore. Right? It can handle all of the real-time data coming from mine production systems, gas and ventilation, environmental data, all of our online systems for machinery, and more importantly, our personnel that are actually cutting the coal. In terms of non-spatial data, we often get, and it's key to the risk management processes that we have for underground coal, that we test for gas content within the coal that we're about to mine. All of the laboratory results are put out in proprietary formats coming from the laboratories, and trying to align and incorporate that into our systems and processes is a tool, as a process that FME is really ideally placed to do, because we don't rely on the specific proprietary softwares that a particular lab or a particular mine site uses. Again, in planning files, other flat files, CSVs, that sort of thing, or any tool-specific data or code that the mine happens to be using, there is typically always an FME reader or writer that can provide the translation to allow that to be aligned with the rest of our spatial data. Our spatial data comes from various forms: survey drawings, CAD drawings, downhole logs, seismic surveys, and other tracking and machine logging systems. All of those data sources, as we work from bottom to top, need to be incorporated and stored into eventually a well architected, should I say, data model. And the format and the architecture of that data model is key to allow the flexibility and analysis that, that we need to be able to analyse these emissions correctly. So, as I was saying, data-driven culture, really the key, and FME can help with that. We like to make decisions based on fundamentals, facts and data, without placing the additional burden on the operational staff, particularly at the mine sites. We remain technology and data source agnostic, and FME really allows that automation and systemic data processing with the improved resolution in both space and time. While doing that, we also allow the reporting and presentation layer to be completely agnostic. And that's one of the benefits, the major benefits of the FME platform, in being able to provide that agnostic deliverable to the mine site client so that it can be displayed in their system of choice. So today I'm coming to you from the Illawarra region. It's steeped in history of coal mining. The mining of coal, particularly coking coal, coming from this area is critical to the regional and state economy. Access to the coal and the limestone used in steelmaking was one of the main reasons for the location of the Port Kembla Steelworks here in this region in the early 1930s. So Sydney on the right of the screen, with a study area of approximately 100 kilometres by 100 kilometres, can be viewed in products like Google Earth, which is shown here, but typically that's only a surface and above view of the world. Sometimes we get the benefit of bathymetric imaging, but the coal measures that we're actually looking to investigate and research are actually at depths anywhere between 300 and 600 metres below the surface. Right? These particular coal measures, as we see in the strata column there on the left of the screen, are typically of Permian, late Permian age, right? And they're all, apart from some outcrops in our local escarpment here in the Illawarra, they're typically at depths and unable to be visualised in products like Google Earth. So how do we visualize those subsurface features? Well, essentially we look at, particularly at a regional scale, we look at all of the different data sets that we've got available to inform visualizations like the one that you're seeing on the screen. Our research has determined that the high resolution, depth of cover, slope, aspect and curvature data is critical to the fundamental calculations that are needed for gas emission prediction. Specifically, we've observed a very strong relationship between the areas of very large variation in horizontal stress magnitude and orientation and the reported outburst occurrence. But how did we extract the required data? And more importantly, how did we prepare it in order to visualize it like is shown on the screen? So, as I mentioned, a lot of the boreholes are coming from data that was done many decades ago and often stored only as scanned originals in things called a well completion report, a WCR for short. So FME has allowed us, using the optical character recognition, to clean those images and import the key data from those well completion reports into Excel, where we can then validate both the strata intervals that the boreholes have done and also convert, in a lot of cases, feet to meters and previous coordinate systems into our MGA 56 zone coordinate system that we use here for the east coast of Australia. From that, FME allowed us to produce 3D lines and also points where we can add the strata geology or remarks as attributes and join all of those 3D points to create 3D polylines that you see on the right of screen. So some of the key transformers that we used to undertake that processing within FME, as some of the earlier speakers have mentioned, we're a great fan of the attribute manager. It's very, very flexible, versatile transformer, and a lot of the calculations that we do can actually be done within the attribute manager transformer. The other specifically that we're using in 3D representation, like we have here, are the extruder and the line builder. And they really help us to put this into a form that's easily transferable to site so that they can see exactly what's going on with their historical exploration data in 3D. So in regards to some of our digital elevation models that we're using to underpin those visualizations, again, FME comes to the fore. We're using the best available vertical Z resolution data that we have. Ideally, that's 3D points and lines, but can go anywhere from interpolated contours through to other exploration data, seismic data, in particular the geophysics that are produced by some of the more recent and contemporary exploration rigs, and also what we call DGS data, or drill guidance system data, that typically takes survey reference every 6 meters in the case of underground horizontally drilled boreholes. From that best available data, we create the digital elevation model surfaces. We use a spline interpolation of Z using minimum curvature, and we incorporate into those calculations any structures that we know about or have been found by the exploratory drilling, and we incorporate those as barriers into the creation of the digital elevation model. Measured values are always used in preference to interpolated values, but we can get down to very, very high resolutions, as much as 1 meter by 1 meter. But certainly that sort of resolution is not required all the time, and that's where things like both reprojector and also downsize of sampling using FME can also assist in creating that balance between data size, speed of processing, and the resolution actually required to do the analysis. Using those digital elevation surfaces, because they're fundamentally a raster-based calculation with your coordinate system built in, all of the other spatial properties in relation to either depth of cover or also the surface or underground floor seam levels. All of those other properties, like the slope, the aspect, the curvature, distance to various and vectors to different features like structures, local minima in terms of any sinks or effectively watershed calculations, can actually be done within FME using raster expression evaluators in most cases. But I'll also point out there's been some recent work done by Greg Patterson, also as a member of the FME community. He's put a transformer on the FME hub called the Aspect Slope Creator, and that actually is founded on some work that Esri did in the previous years, which gives a really good visual representation of both the direction and the degree of any slope that may be pertinent to the calculations that we're doing. So all of that put in raster-based form allows AHD common Z references. It allows surfaces to be calculated on the fly. It allows each of the relevant seams or strata intervals to be done with raster-based processing, which typically is a lot faster than any vector-based processing for our form of analysis. I will point out all of that needs to be done at an appropriate level of resolution for the analysis and the calculations that you're doing. In terms of some of the really messy data cleanup that we're able to do with FME, I won't go through this in length, but I understand there will be a copy of the both the PDF and the recording of the presentation made available to participants. But some of the things that we're doing with particularly historical AutoCAD mapping, is really something that only a tool like FME could do, because a lot of the data is actually incorporated only as text into the CAD file. Things like geometry filter, feature joiner really come in, but the most common one that we're using for those historical ones is the neighbor finder transformer. It allows a lot of different things to be done with validation and manipulation of text, creation of the necessary attributes to really provide well-structured and attributed geometry on a common coordinate system that reduces a lot of the opportunities for error downstream. And that also applies with all of the different horizontal inseam drilling and survey and calculations and analysis that we're doing more recently. Over a number of phases, we've eventually developed tools to allow complete 3D recalculation of drill guidance system data on the fly. So as that data is coming off the machine, typically is stored as 6 meter interval survey shots, and we have proprietary workspaces now that completely remove any of the workload from mine site staff and incorporate that drilling geometry into a 3D visualization for use at the mine by the operational staff. Down at the microscopic level, we're also looking at the particular inseam properties, and that's where really the CT-based analysis that we've had available here at the University of Wollongong to really look closely at the variation that occurs in the coal within the working seam in particular. In a lot of cases previously with historical gas calculations, generally only one value is applied to the entire seam, which may be up to, in the case here in the Illawarra, up to 3 meters thick. But as you can see from the representation there on the left-hand side, that's actual coal lump blocks that we've taken from a range of different sections within the working seam. And we've done the CT analysis on that to provide a density-based arrangement where we can actually see the individual properties of the layers which follow the geochronological sequence within the mine from the working seam floor up to the working seam roof. You can see a representation of that in the top right of screen. That's purely based on density, but they're also a key to understanding particularly the coal properties in terms of its ability to pass gas, right? And its permeability and how that material behaves in response to the horizontal stresses that are applied not only over geological time, but also as part of mine production and extraction. So some of the tools, and they're available in the link, I might put that in the chat there. With the help of Dimitri at SAFE, we created a workspace which actually converts the DICOM format images produced by the CT scanner and convert that into a 3D visualization of the different material properties. Again, it's only density based, but that density base allows us to really hone in on where we're going to get specific permeability within particular layers. And those that understand even some basic physics, even if you have one very highly permeable layer within a 3 meter coal seam, the gas will naturally try to travel through that highly permeable layer first before it tries to get in any of the others. And that's particularly important in an outburst condition or situation where it's that dynamic release of gas in a very short space that allows the analysis to be done correctly. So why do we want to democratise this data? Well, those showing on the screen there, some of those things are, it's all really about providing a safe working environment and safe systems of managing risk. The more people that have faster access to that critical information that's required for the decision making, the better. The validation can be incorporated into the key management systems to automatically flag for these dangerous conditions and hence avoid the situations like are displayed here on the screen. Both are the result of gas outbursts. The result of the gas outbursts on the longwall face on the right, over 100 tonnes of coal were ejected into the supports that you can see on the right-hand side. Fortunately, no one was harmed in any of these incidents, but it highlights the importance of having the data needed to make informed decisions available to the operational staff in a timely and consistent fashion. Some of those, particularly in the with the readers and writers that are available in FME, allow us to democratise that data in a very platform agnostic way. So some of the things, and I'll just quickly allow some of the video here to play in the background while I'm talking about it. But some of those systems, increasingly the 3D PDF is one of those that the guys on site really love to be able to visualize exactly what's happening in their workings underground. The 3D format, if you correctly attribute and actually create the geometry in 3D and correctly store that in a well-founded data model, really makes analysis and presentation of that data at the top level of the iceberg so much easier, while all the heavy lifting is done by FME in an automated and systemic fashion. So some, I think I put up previously a visualization of the both the Earth's surface in the Illawarra region and also some of the underground features that we're looking at in the working seam, which is predominantly the bulleye seam here in the Illawarra. And as we go around the video, those 3D poly lines, which we created with the help of FME, combined with the surface imagery overlain on the surface digital elevation model with a high resolution depth of cover relationship. So we've used Esri Arcscene in this particular example, but it's FME under the covers, which allows visualizing of this data and presentation in a easily consumable way to all of the people on site. Some of the horizontal drills that we've got all of the DGS data that I mentioned previously. This one is shown in 10 times vertical exaggeration, but it really allows the drilling operators to really get a handle on the trajectory of the drills in 3D using the survey coordinates that are sourced directly from the drill rig's guidance system. So as I've mentioned earlier, proprietary systems in FME have been developed to allow extraction and processing of that DGS data directly into the visualization that's shown there. Further work in this area includes the rendering of the precise locations where gas samples, core samples, have been taken for the mine for gas content testing to really allow that alignment of all of the field data that we're taking. Some of the things that we're doing with the GLTF format in particular, it's increasingly portable, can be read with a standard Windows 10 3D viewer. Some of the different visualization techniques that are used here, we've got extrusion or the height of these little pillars representing gas content. We've got the color of the pillars representing gas composition, black pillars representing recorded historical outburst events, and the surface representing the floor of the coal seam with vertical exaggeration, but the color and the shading representing the slope and the aspect that we've got, which really are now allow the operators to see exactly where they may be running into trouble. Some of the things that we can produce and use the FME and the Mapbox platforms to do. I'll just quickly put this in here. Again, the composition is rendered as the color, but the FME platform really allows the creation of the data model, which makes the presentation in tools like Mapbox and Power BI. It really makes that simple, straightforward, and easy for the operators to consume. Some of the things that we can do only by a correctly structured data model include assessment of all of the different coal parameters that we've got to analyze and assess the different types of gas compositions, gas contents, and really assess the risks associated with those mining areas that we're about to enter or about to mine. And presentation in tools like this makes it really, really easy for the operators to consume and understand exactly what's going on. So in conclusion, over the last 7 years of research, FME has really been critical to the treatment of the data from the multiple disparate sources that we've had to deal with at both regional and through to the microscopic scale. Using structured data is really fundamental to robust and accurate gas emission modelling at both the high resolution in space and time that's required to do the analysis correctly and consistently. Maintaining those vendor agnostic workflows avoids significant risk in production and, of course, vendors either changing their pricing structure or changing their business models, which has the potential to incur additional cost. By keeping those workflows inside FME and correctly allowing that automation to be based on an input data set, a processing set, and then a storage or output set, it allows that avoidance of any of the risks associated with change of vendor business model. But finally, the democratization and the visualization of the data that we've got in various forms really allows that decision making in management to be driven by the fundamentals and by the data. Thank you all very much for your attendance today. I'll just see on the chat if there are any questions. I see I've got around about 77 attendees. Wow, that's amazing. I hope the presentation was informative and people got something out of it. If there are any questions at all, please just pop them in the chat, and I'll do my best to answer any of them that you may have. I see lots of thank yous and congratulations in the chat. So that's great that people get something out of the presentation. I hope it sort of underpins some of the fundamental data based processes that are actually required to do this in an operational, in particular, a mining production setting. It's so critical to keep well-structured and consistent data in a well-architected data model to allow the type of analysis that we're doing. It wouldn't be possible without tools like FME and the range, as I think Mark has pointed out, the range of different transformers that are available and the flexibility that the platform provides really allows us to take our research to the next level. If there's no further questions, I think I might stop the recording there. My contact details are in the slide, and I'm sure the presentation will be shared in various forms by Locus at a later stage. Thank you all.